Good afternoon to all of you, and welcome to this lecture of DIP. I think it is 15th lecture. In this lecture, I'm going to talk about frequency domain image processing, and basically, we are going to use Fourier series and Fourier transform to get into the process. I'm going to introduce this topic in a very brief manner. You all can read further on this topic and we can discuss in the post lecture discussions as well. So first we are going to talk about the Fourier series, and then I will in short introduce something called as Fourier transform. We will look at how would a two-dimensional Fourier image transform equations look like, and how do the spectrum look like, and we will talk about frequency domain filtering fundamentals like a low pass filter, high pass filter, and notch filter. I hope you all can hear me clearly and see my screen. If there is any issue, you can always text me back. So Fourier series, as we all are familiar with it, I'm sure all of you have studied this in the lower class. J.B. Joseph Fourier, born in 1768 and died in 1830, in France, presented a mathematical tool by which any periodic function can be expressed as a sum of sine and or cosines of different frequencies, each multiplied by a different coefficient. And this statement or this sum we call now as Fourier series. I'm going to show you its mathematical form also to you. It does not matter how complicated the function is. It could be any shape as long as it is periodic and satisfies some other conditions, few conditions. It can be represented by such a sum. Functions which are not periodic but whose area under the curve is finite can be expressed as the integral of sines and cosines multiplied by a weighing functions. This formulation, which is the next step from the Fourier series, is called Fourier transform. This has enabled us to simplify many problems in physics and mathematics and signal processing and many other branches. So what has happened is there are complex waveforms, complex signals. Even human voice is a very complex waveform. But all communication systems, when they are tested for sines and cosines, then combination of those sine waves and cosine waves can produce any complex waveform. So once the system is tested for a given band of sine and cosine frequencies, we assume that it will also work with human voice. So a complex process of testing of human voice can be simplified in electrical communication systems. And similarly, many other places, Fourier series has found its application. Originally, he was working on heat diffusion in solids, and that's how he had arrived on this configuration. So it is one of the most important discovery in mathematical physics in last 200 years. The Fourier's name has been etched on the north face of Eiffel Tower. So these are the names which are etched. They are all in one row. The row is very long, so I broke it and presenting here in two parts. If you look at the Fourier's name is over here. If you look at some other important name, one important name is which is very important for us is of Daguerre. The Daguerre was a person who is considered as the person who invented modern photography. So he was the chemist who actually prepared the formulation by which an image can be transferred on a glass plate. And image processing began after that. So for us, very important name Daguerre. Since we are also physicists, there are a few more names you can remember. You can see here over here. D'Alembert, famous for his uh, principle of virtual work. Malus for his laws on polarization. Clapeyron for his Clausius-Clapeyron equation. And I think one or two some more names are there. Carnot is here for Carnot cycle. So what French did was they took the names of their most famous scientists and put them on the Eiffel Tower on four sides. Imagine if the Eiffel Tower had been made in India, probably most likely it would have been named after some politician. So that's the difference. Okay, so let's get back to Fourier series. A Fourier series, as I said, is the sum of sine wave. This is a very complicated looking function, but you can see that it's a periodic function. This is one period, so on and so forth. It can be shown as the sum of multiple sine waves. So this is one, then this is another, and then this is third, and these are higher frequency. This is low frequency. As you go up, the frequency becomes more and more and more. And when you add up all these things, remember this will determine your base period. So this base time period, distance between here and here, is determined by the fundamental frequency, this one. The rest will determine these small protrusions up and down. So all these. So this is how this Fourier series enables us to visualize this complex waveform into its simple components. And typically a normal Fourier series is written like this in complex waveform notation, which is simple notation. In fact, remember e power I theta or j theta is cos theta plus j sin theta, where j is the imaginary number root of I. So what you have over here is, you can see that these CNs, and this is a sinusoidal series. Just to tell you, this is the time period, time after which it repeats, and n is the number of samples that you take, and this or number of terms of the number of terms in the series, and this will go on. If you expand this, you will get a cosine term and the sine term. Sine term is imaginary, you can discard it and write it in the form of cosine. Each coefficient can be obtained by this integral. So you have this integral and you obtain each coefficient. So this is the general way of writing Fourier series. Fourier transform, on contrary, is written in this form. So your function, you put the function over here, multiply by e power minus j 2 pi mu t dt, where mu is frequency, t is time period, and you get a function of frequency. One can see that if you put the function of frequency here, make this minus as plus, then you get a function of time back. So it's symmetric in that sense. So presented this way is called Fourier transform. This is going to be very, very useful for us. This is a Fourier transform that converts a time domain signal into a frequency domain signal. And this is called inverse Fourier transform, which converts a frequency domain, mu represent frequency, so frequency domain signal into time domain signal. I'm not getting into the details of it. I'll tell you the reasons why. But before I tell you that, let me recall where you have studied it in your lower class. I think I remember, if I look back, I remember at least two distinct occasions where you have studied Fourier transform apart from the place where you have definitely done it. So for example, all of you must have done AM wave, amplitude modulation wave, at some point in your studies. Now you know that an amplitude modulation wave is the sum of three frequencies: the carrier frequency, the upper sideband, and the lower sideband. So if you have upper sideband, lower sideband, carrier, all three added together, you get an amplitude modulated waveform. So your amplitude modulated waveform is a time domain signal. Your actual frequencies are frequency domain signals. Then the other place you must have done is the beat formation. Beat formation, again happens the same thing. You have two frequencies which are close. So they form your frequency spectrum. And your time domain signal is your formation of beat. Apart from this, you have done many others. Like you know that if you have a square waveform, then the it contains odd harmonics only. So you have done those applications. So this is time domain to frequency domain. Now remember what we are talking in terms of time. When it comes to image analysis, then images are not a function in time. They are the function in position. So when you come to the image part, or when you apply Fourier transform to image analysis or DIP, then time is replaced by position. And this is frequency. Frequency has the dimensions of 1 upon time. So in the image analysis, the frequency will have the dimensions of reciprocals of position. So reminding you again that when you apply it to image analysis, the time is replaced by position, and mu or frequency is replaced by reciprocal of frequencies. Now instead of giving it some new name, we still just call it frequency. But what we mean is how frequently the object in an image repeat themselves. So if they are repeating themselves very often, then we say that they have high frequency. And if they repeat themselves not that often, then they have low frequency. Obviously, in any image, small object or smaller the object, the probability that it will repeat itself many times is more. So the frequency will be high. So smaller objects, smaller parameters, smaller features in an image has high frequencies. One example is noise. Noise is very small, sometimes at the pixel level. Frequency is generally very high. While on contrary, larger objects have lesser frequency because they are going to repeat themselves lesser amount of time. So, or lesser number of times in the given image. So that is how we, sorry, that is how we modify the Fourier transform, which is in time and frequency domain, to position x and 1 over x domain. So remember, this I would still call as frequency, but it is reciprocal of position. So the other change that will come from here to here is this, that the time domain signal can be a continuous signal. Going back a few slides, look at this. This is a continuous signal without any break. It goes on and on and on. Images are not like that, and especially digital images are not like that. Digital images are sampled signals. They have pixels. Each pixel has one value for some space, then the value changes. So the other thing we need is, so one thing we needed was converting time into position, mu frequency into 1 over position. Other thing that we need to change is a continuous integral into a discrete summation. So we do that. And remember the limits here, minus infinity to infinity. I theoretically a signal, time domain signal can spread from minus infinity to plus infinity. Practically it will, an image will not. An image will go from one, some maximum number of pixel from x is equal to 0 to some maximum number of pixel, and f of x gives you the value or intensity value of at a particular position x, and this is what is called discretized. M is the total number of pixels in the given dimension, and this is called discrete Fourier transform, which is used for operations in image processing. So we have made three changes. One is we change this x time to x. The other one is frequency to 1 over x, which I'm calling it as u. We would still call it frequency, but do remember it has dimensions of 1 over x. And third is an integral. Images are not continuous functions, they're discrete functions of in the space. So integral to summation starting from 0 to a maximum value of m minus 1, no longer minus infinity to infinity. You don't have an image which spreads out that much. So this is your discrete Fourier transform. This is called discrete Fourier transform. While if I take it, bring this thing over here, bring this thing over here, instead of minus I put plus, what I will get, and you need a normalization function 1 by m. If you do more mathematics, you will realize more about it. Sometimes it's written as 1 by m, or sometimes it's written as 1 by root m here and 1 by root m here. Part of a mathematical work rigor that you will need for this. So normalization is needed in both actually. All I'm trying to tell you that still symmetric, but if you write root m here, you will get 1 by root m here. So with these changes, you can see that this brings you your inverse digital Fourier transform. So here you have an image which is in the frequency domain f of u. You apply the inverse Fourier transform and you get into spatial domain. Here you have an image in the spatial domain. You apply a Fourier transform, discrete Fourier transform, DFT, and it will bring you, or it will give you the frequency spectrum or frequency image. This just one small thing is still remaining to be changed, and that is most of the images will be a two-dimensional function and not one-dimensional function of position as it is shown over here. So we convert, or we would need in fact a DFT or a discrete Fourier transform which is in two dimensions. So we modify these equations further and we convert them into Fourier transforms of two dimensions. So you can see that now instead of only x, we have x comma y. Instead of only from m 0 x is equal to 0 to m minus 1, we have y is equal to 0 to n minus 1, where m and n are maximum number of pixels in the image. Even this goes into two components, and this also is two components. Rest is similar. You have f of xy here. Operate f of xy with all these things, and you will get an image in the Fourier domain. You take the image in the or frequency domain. You take the image in the frequency domain. You operate an inverse discrete Fourier transform, and you get an image in the spatial domain. So this way you can get your discrete Fourier transform. Now the question is that why am I doing it not in much detail, and I'm just keeping it at all these equations at the mathematical level. So why I am doing this is very straightforward. Most of these things you will be doing or you will be implementing by computer software. So most of the softwares on Fourier transforms are pre-ready. and you don't have to reinvent it. Remember, all DFT algorithms are available, and in fact, there is an algorithm available on DFT which is now called as FFT, which is fast Fourier transform, which is very fast compared to the earlier algorithms. So from mathematical point of view, if you are interested, you can explore them. But for image processing point of view, all we need to do is just have a brief idea about how to use the equations and what are the equations which convert a spatial domain signal into a frequency domain, and how a frequency domain signal goes back into spatial domain. That is all we need to understand, and rest we need to understand is the use of the software, how to use software to achieve what we want. So in the next part of the lecture, I'm going to talk about that. So to begin with, my first image today is a rectangle. This is a very simple image. You can see that rest is black, this is white. You can have, or you can have a binary of, this image as zeros put everywhere and one put in the middle or the center. So this is a rectangle. If you take this image and use these two equations, use the upper equation. So take each values of pixels at each location, perform the operations with this, and you will get a function of u and v, which would look like this. Sorry. So look at this. Do you find that this is familiar to you? Have you seen it anywhere? Recall your early physics training, and if you think hard, I'm sure that all of you have seen this. You can tell me by writing it what it looks similar to. Think hard. I'm sure all of you have studied it either in your higher secondary or undergraduate levels. You might get it. If you think carefully, you would realize that this is nothing but the diffraction pattern. This thing looks like a slit, and slit illuminated, a vertical thin slit illuminated by a light source. Yes, Pinak, you got it correctly. And this gives you the diffraction pattern. Remember, the diffraction pattern is actually in two dimensions. So you will get a diffraction pattern here, and you will get a diffraction pattern this way also. Just that since the width is very little, you get more prominent bands in your calculation. Width is more here, so it is less over here. Yes, it is the diffraction pattern. Diffraction pattern offers any image or any slit is nothing but the Fourier transform of a similar image. So there is this very strong correlation between optics, Fourier analysis, and the Fourier analysis in the image. So if you calculate, you will get the software. You will generally, if you make this kind of image, for example, you can use a PowerPoint tool or some tool like that to create this kind of an image. Crop the image. You have image J, Fiji image J, you feed the image J, find the Fourier transform, you will get this. But as I said, you should also get some component here. These are not visible because their values are too little. And generally, if you apply some sort of gamma correction now you are familiar. So you apply gamma correction and you will get this one. So this is how the pattern looks like. This is the Fourier domain image. This is spatial domain image. This is what you get after you apply the first equation. You apply this equation, from here you get this one. This, remember, always Fourier image may not be very visible. As I said, large components are not so visible, so you may have to put some contrast gamma correction. One can recall that this is a pulse function. uh, if you do mathematics, it is presented in the Gonzalez and Woods. And if you do mathematics, this is a pulse function, and Fourier transform of a pulse function is a series of sine waves. So this is fundamental sine wave, this is first harmonic, second harmonic, third harmonic, fourth, so on and so forth. There is a pulse in this direction also, so there are multiple sine waves being added. So that is how the Fourier looked like. Okay, you can do some corrections to it. I'll come to it later. Now if I shift the rectangle without tilting it, you will find that the spectrum remains the same. This was the spectrum in the previous slide and there is no change. So it does not matter. So a Fourier transform generally, or a Fourier image generally cannot predict the exact position of the object in the image. So whether the spectrum, whether the slit was at the center or it is shifted, you will not find that difference. You cannot look at this and say that the image is shifted. This was the previous, this is the Fourier transform from the previous slide. This is the Fourier transform of this one. So you cannot find the difference. So what lesson we learn is, wherever is your object in the image, the Fourier transform will always be at the center. It will always be in the middle. So please remember that, because when you do the actual analysis, it will be helpful. Lowest frequency will always come at the center, and then symmetrically it will spread in all possible directions. However, if you tilt the image, then you will find that the spectrum will tilt. So this is the thinner side now, so its diffraction pattern will go in this way. So that is how the image will tilt. So by looking at the tilt in the lines, you can always guess, or you can always predict the way the objects are tilted in the original image. So position of the objects in the original image you cannot predict by looking at the Fourier transform, because everything comes to center. But the direction in which they are tilted, that you can always predict, which way they are tilted. If this image is a complicated, that was very simple. This is more complicated. You can see that you can easily guess the Fourier spectrum. Remember, first thing, position of all the important objects. This is one object, this is another, this is third, this is fourth. All will come to the center. So all will be originating from center. Secondly, if the object is linear, the spectrum will be perpendicular to it. So this way. Now there are lines this way, so spectrum will be this way. But this is one thing which has gone apart, some other direction. So that line will appear in this way. So we can see the spectrum, and you can see here is the spectrum. This has lots of lines which are inclined at 45 degree approximately. So this one, this one, and this one. All these will give me a very strong Fourier component in this direction. Then it has a lot of lines which are inclined on this side. This is one, and this is one, and this, and this, and this, and of course this part. So this will give me a Fourier in this direction, perpendicular to it. But what is this dotted one? So you can easily guess that this looks perpendicular to this feature, this object. So if this is my object, keep it here, it will become perpendicular to this one. So that's how the spectrum of a complicated image look like. So looking at the spectrum, you can guess that how the objects are placed in the image, how strong they are, how weak they are, even that can be guessed to an extent. For example, you can see that these lines are, and even this one, are very strong compared to any other line. That means it says that these lines, there has to be strong diagonal lines in the image. Now we can go to the filtering part, that how do we do filtering in the frequency domain. So frequency domain filtering somewhat is like this. You have a frequency domain image. This, remember, this is UV. You apply the filter to it. Filter is also a function of U and V. That means you are applying the filter in the frequency domain. And once the filter has been applied, you can run an inverse Fourier transform. Again, as I said, calculation yields complex numbers. You discard the imaginary part, hold the real part, and that should be your image. So the entire process HUV is filter transfer function. So the entire process looks like this, that you start with image domain, that is spatial domain, f of xy. You apply a discrete Fourier transform. Applying discrete Fourier transform will give you the frequency domain image, which is in U and V. Then you apply your filter. You process it in frequency domain. So apply your filter, whatever filter H you can apply. And after that, you take the inverse discrete Fourier transforms, IDFT, and get the final results in the image domain once again. So this will be your G of xy. So that is your general procedure to carry out the Fourier analysis. So let's see some of the filters. Three filters I have here for us to discuss today. The book discusses a couple of more and you can go through them. So what is an ideal low pass filter? So a low pass filter, ideal low pass filter is, uh, it allows certain frequencies for up to the distances up to those pixels which are less than a critical value, and it will not allow the frequencies which are greater than a critical value d0, where d is here is a distance from the center in the Fourier image. Do remember that. I'm going very slowly. Try to uh, pay attention. So this is an ideal low pass filter. So you multiply your Fourier image or Fourier transform image by 1. So when you multiply by 1, there is no change. It remains the same. But when you multiply by 0, then everything becomes 0. So you delete all the values beyond a particular distance d0 from the center and retain all the values which are within the distance d0. This will form an ideal low pass filter. As I said, d is an Euclidean distance. We have already learned this long back. Graphically, this is how it will look like. This is H plotted in UV plane. Remember, we have here the filter is designed and applied in frequency domain, which is UV plane and not in XY plane. So this is the center of your UV plane. All these pixels which are at a certain distance, say from this is center, from here to here, they're all retained in this. So this value is 1, rest is 0. So all you have to do is multiply H to the original image. Other way to visualize the filter, this is I'm talking about visualizing filter. Other way to visualize the filter is in between as a black and white. Black represents 0, white represents 1. So if you multiply this mask to the image, the Fourier image, then it will make all the components 0 which are in this region, while it will remain, but it will leave this part unaffected. The third way to visualize is a graph plotted from center to as a function of distance. So at d0, between before d0 it's all 1, so no change. After d0 it's all 0. Big question is, what decides d0? And to answer that question, d0 is decided by the user. So you have to decide that how big this filter you have to apply. So if you shift D0 here, then this circle will become bigger and lot of frequencies are retained. If you apply D0 very close, then very few frequencies, very small, then very few frequencies will be retained. So let's take an example. An example can make you understand better. So I have my ideal low pass filter 10. This is how it looks graphically, we have just seen. Now let's take our standard image. Remember, we use the same image even for the spatial filtering, and I had demonstrated you how it works. Here objects are thicker, so the frequency is high. As you go towards periphery, the lines are thinner and frequency is less and less possible. Okay, so now let's take its Fourier transform. So if you feed it to a Fourier transform function, FFT, DFT, whatever, you will get a Fourier image. So this is the Fourier transform of this image. If you look at it very closely, and you can't do that, I did not do that correction of gamma. If you look at it carefully, it comes in the concentric rings also. Why does it come in concentric rings as compared to earlier where there were only lines? The reason is here there's concentric circles. So each circle is like a slit rotated by 360-degree, and that's why you will get concentric circles in the Fourier image also. Now I want to apply this filter to this. So this is my filter. If I apply this, means I multiply the filter to the image. If I do that, then I retain the central part and the rest will become 0. Just to remind you, this is not to the scale. I mean, the scale has been changed while multiplying. This has become smaller over here. So very small center part has been retained and rest is made completely 0. Now you take the inverse Fourier transform of this image, which is your processed image in frequency domain. You take an inverse Fourier transform and you get this. So what do you get? Look at it carefully. You will find that the peripheral frequencies are vanishing. These frequencies will blur out, will go. Okay, so this will vanish completely. So you can see you took your image in image domain, applied the Fourier transform, you applied the DFT to get the Fourier transform, applied the filter, and then finally you take the inverse Fourier transform. Since this is low pass filter, you got some rings, low frequency objects retained in final image. High frequency rings are suppressed completely. Where to stop? Where would you stop? That decides how big this filter is. So if your D0 is large, then you will take many lines inside. If your D0 is very small, then you will eliminate further lines on the periphery. Why does the image look like it's moving the main image towards the extreme left? That's a optical illusion, Abhishek. Very standard optical illusion. Maybe post lecture we can discuss about it. Nothing to do with image analysis here. So yeah. So let's take a Gaussian low pass filter. Gaussian low pass filter equation is this. Typically, this is a variable, this part, but right now D0 has been kept. How it differs from a ideal low pass filter is the in gradation, depending on there it was bright and then suddenly to zero. Here it will vary smoothly. The line is no longer vertical, it has a slope. Slope is decided by the value of d0, how many pixels you choose from the center. D0 is the distance from the center. So that is how a Gaussian low pass filter is designed. I'm not giving you an working example of a Gaussian low pass filter. Maybe you can try it on your own on the lines I have shown here and check it. Or maybe we can discuss it later. I will introduce a high pass filter. Remember all high pass, just before I talk more on high pass filter, we also talk about there is one more filter which has been discussed, the Butterworth low pass filter. Please go through that as well. A high pass filter, all high pass filters are 1 minus low pass filter. So an ideal high pass filter is 1 minus low pass ideal filter. So 1 minus 1 will give you 0, 1 minus 0 will give you 1. So all the frequencies up to distance d0 are passed, rest are, sorry, are stopped, rest are passed. This is an ideal high pass filter. An ideal Gaussian filter would look like this one. So this was, remember, the ideal low pass Gaussian. 1 minus low pass will give you high pass. I will show you a working example of a high pass. But before that, okay, this is the graphical representation. Look at this high pass. Remember in low pass, surrounding was black, center was white. Here it is reverse. While in Gaussian, these variations are smoothened out. So again, you multiply this or this to an image and to the Fourier transform of an image and then get the processed image. So I'll show you one example. This is high pass filter. This is my filter, black in the middle, white in the surrounding. This is my original image as usual, as we had discussed. This is the Fourier transform. We already spoke of it. Now I apply this filter to this. Remember, this is again not to the scale here in this one, but the application was done by making it to the scale. When I do this, I will eliminate the central frequencies. So I will apply the filter to the Fourier transform. So multiply each element to this. You will find that wherever these zeros appear, those frequencies are eliminated completely. They are removed. What decides how big is this dark circle? That is decided by the D0. What is D0? Distance from the center. Who will set this? User will set this. User will decide how many frequencies I want to block in an high pass. So all lower frequencies are blocked, higher frequencies are retained, you can see. So this is the higher frequencies and this is the inverse Fourier transform. You can see that all large objects from the image are suppressed completely, while all finer high frequency lines are retained. Where to put the cutoff, that is decided by D0, which is in turn decided by the user. This should be, what I have used is around 30 pixel diameter, 30 pixel diameter over here. The entire image was around 700 pixels approximately, 700 by 700. This is a 30 pixel, 60 pixel diameter, 30 pixel radius. Sorry. So if I increase the diameter further, it will eliminate more lines from the center. So this is how it works. Another example, and which is the last example for this lecture, is the notch filter. A notch filter can be useful in this kind of image. So look at this image. Look at the noise. All these are small dots are noise. Please try to identify. Next chapter we are going to talk about noise reduction and we will revisit this idea. If you observe it carefully, it looks like a periodic noise. Now what is a periodic noise? A periodic noise is one which repeats itself at some frequency or some interval. Here the interval is in space. So this is all periodic noise. One is this direction and one is this direction. There is some periodicity vertical and some horizontal. So these are small scale features, high frequency features. While low frequency features in this image is the structure of the car, the wheel, etc., the large scale structure, and these are little bit again small scale structures here. So this is my image which is corrupted with, if I can see, a periodic high frequency noise. I want to remove these noise. So the Fourier domain frequency is one of the best tool to reduce it. Reducing this is a very tough job by using averaging or spatial filters. Because in spatial filters, you will also eliminate the structure of the car, the sharpness on the car also, but not in the frequency domain. So in the frequency domain, the moment I take a Fourier transform, what I will see is very interesting pattern. What I would see is these stars appearing. Now these stars, remember, they are away from the center. Since they are away from the center, that represents that they are high frequency. Again, trying to recall, towards the center frequencies are low, away from the center frequencies are high. So the these are high frequency, high frequency, high frequency. So all I can do is I can eliminate those high frequencies. So these are, if I do that, I'm creating a notch. I'm eliminating just one particular range of frequency. So these are called notch filters. Notch filters located at different frequencies. Multiple notch filters I have applied to the processed image, and then I take a inverse Fourier transform and I get this. Now if you observe it carefully, most of these patterns have vanished. They have already gone. Some traces are here and there remaining, maybe some more analysis. But interestingly, look at the sharpness of the the structure of the car. It is retained most of the places, which will not be retained if you are using what is called uh, say a spatial domain filter, like a box filter, kernel, something like that. So that is how a notch filter helps to eliminate a particular frequency of noise from the entire corrupted image. So yeah, we can stop here. Thank you. I will come to Google Meet in a minute.